In this video, we're going to do something very exciting. So if you've learned about Laplace transforms, you might know that the main reason that they're typically used is to solve differential equations, is to turn differential equations into algebraic equations, which then allows you to solve them, and then you can turn it back again in terms of the differential equation, and then, hey presto, you've solved it, nice. But actually, something that's kind of obvious when you think about it, but people don't really think about it that often, is you can actually use these Laplace transforms to solve lots of integrals, to compute and evaluate integrals. So for example, if you look at this one here, you can see that it kind of looks like a Laplace transform, right? Because actually this looks like the Laplace transform of sine, and I'll go in terms of t here, sine of t, and instead of with an s, we're just saying that s is the number 1, right? So it looks like the Laplace transform of sine of t, but evaluated when s is the number 1, right? Let's just remind ourselves what that really is, okay? So the Laplace transform, I'll do it down here, the Laplace transform of sine of t, remember, is just the integral from 0 to infinity of sine of t times e to the minus st dt. That's all it is. And if you can see that in yellow and you look at the one that we've done, they look really, really similar. So what I'm saying is you can actually look at a lot of integrals that are of that form, the integral from 0 to infinity of f of x times e to the minus something x. If you see an integral like that, you can potentially do it with Laplace transforms really, really, really quick. So let's actually do this one. It looks like the Laplace transform of sine t evaluated when s is 1. And remember, that's when s is 1 because here we've got e to the minus st, or x, whatever the variable of integration is. And here we've just got minus 1. So s is the number 1. So let's write down what the Laplace transform of sine t actually is. Remember, that's 1 over s squared plus 1. That's what the Laplace transform of sine t actually is. And we're evaluating that when s is the number 1. So this is equal to 1 over just 1 squared plus 1, which is of course 1 over 2, which means that this integral, which typically would require you to do some really messy stuff, integration by parts like twice, and then you guys might know how to do this, but that's really long. But here, as long as we know our Laplace transforms, we've done all the heavy lifting already. So that's really, really quick. Let's look at a few more. This is the integral from 0 to infinity of x e to the minus 2x times cos x. Now, it looks a little bit harder, but hopefully you guys can see that in this one, it appears to be the Laplace transform of t times cos t. And again, this time it's not evaluated when s is 1, but it's evaluated when s is 2. That's what it looks like that it is. And again, I'm going to write this down. Remember, the Laplace transform of t times cos t is nothing more than the integral from 0 to infinity of t times cos t times e to the minus st, okay? Because that's all the Laplace transform is. It's the integral from 0 to infinity of the function times e to the minus st. So that's what it looks like. And you guys can see that's actually exactly what we have got, but instead of s, we've got the number 2. That's the only difference. Now, the trouble with this one is the Laplace transform of t times cos t is not that obvious. And I'm going to write down another little formula that we've got. And I've derived this in a previous video. I've got an entire playlist on Laplace transforms, in fact. But the Laplace transform of t times some arbitrary function of t is minus the derivative with respect to s of capital F of s. And capital F of s is the Laplace transform of just f of t on its own. Okay, so what I'm saying here, and let's actually do this, this integral is going to be equal to minus the derivative with respect to s of the Laplace transform of cos t, because cos t in our question is acting as this f of t. Now, what is the Laplace transform of cos t? Well, it's nothing other than s over s squared plus 1. And all of this, because in this question s is the number 2, all of this needs to be evaluated when s is the number 2. But of course, we can't just plug 2 in yet. We've got to differentiate it first. So of course you can use the quotient rule or you can use the product rule to differentiate this. Let's just use the quotient rule because it's a bit more direct. So this is equal to minus, and I'm going to do a big open bracket here. Remember, the way that you use the quotient rule is you differentiate the top function, so that's the number 1, and then you times by the original second, so s squared plus 1, and then you subtract the other way around. So you differentiate the bottom, which is 2s, and you times by just the original other function, so s again, and then you divide by the bottom function squared, so s squared plus 1 squared there. Okay, and we still need to evaluate all of this when s is 2, which we'll get to in a second. And then we've got a minus, and then let's simplify this, right? So we've got s squared plus 1 minus 2s squared over s squared plus 1 squared. And again, that's evaluated when s is the number 2. And you guys can see that actually, although it's a little bit of work, like you got to differentiate something and you got to remember a formula, it's actually really, really nice, right? So s squared plus 1 minus 2s squared, that's 1 minus s squared divided by s squared plus 1 squared, and evaluated at s equals 2. And then let's do one more step of working here. So I'm going to distribute the minus sign out. So I've got s squared minus 1 over s squared plus 1 squared, and I just need to evaluate this when s is the number 2, and now I can do it, right? So I've got 2 squared, which is 4 minus 1, over 2 squared, which is 4 again, plus 1, so that's 5 squared there. So I've basically got 3 over 25. So guys, let's just look at this for a second, right? This integral looks quite hard, I would say, right? There's a lot of stuff going on in this. This is, I mean, you could do it. You can absolutely do it without Laplace transforms, but blimey, it would be quite time consuming. Hopefully we can all agree with that. But all we had to do was remember a few Laplace transforms. You got to remember some standard results and stuff, and maybe even just use your Laplace transform table if you don't remember them. And all of a sudden, the answer just pops out in really not a lot of working at all. You got to use the quotient rule, and that's it. Really, really cool. Let's look at another one. Okay, guys, this is a really famous integral. This is the Dirichlet integral. I've already got a video on evaluating this. You can actually evaluate it with Feynman's trick, if you know that, but don't worry if you don't. Let's have a look at how we can do it with Laplace transforms. What we have to realize is that we don't have that e to the something t here, but of course we can say that it is e to the minus st, but when s is the number 0, because that makes the number 1. So that's the trick. But what is this in terms of a Laplace transform? Well, this is the Laplace transform, of course, of sine t over t, evaluated when s is the number 0. Now, what is the Laplace transform of sine t over t? I hear you ask in your head or through the screen, or maybe you didn't ask it, but what is it? Let's write it down. So the Laplace transform, this is just in general, of any function of t that you can take the Laplace transform of, divided by t, is equal to the integral from s up to infinity of capital F of u du. Now, this needs a bit of explanation. So capital F of u, capital F, is still the function that is the Laplace transform of lowercase f of t, right? So in this case, capital F of u is the function that sine t Laplace transforms into. But instead of using s, we use u as a dummy variable because we want the whole thing to, as a result, we want it to be in terms of s. So by allowing a dummy variable like u or some made up thing, eventually it's going to get integrated away and then it's going to basically get replaced by some numbers and by an s. So this is the formula. Again, I've got a video on this if you want a bit more elaboration, but that's pretty much all there is to it. So we can go in and we can continue our working out here. So we can replace the Laplace transform of sine t over t with the integral from s to infinity of the function that sine t Laplace transforms into. And of course, we actually just did it earlier in this video. That's just going to be 1 over s squared plus 1. But again, I'm not going to be using s. I'm going to make, because it's just simply because it's bad notation to have a function and then have one of the limits of integration be the same variable. So that's why I'm going to use u. So u squared plus 1, and instead of ds, it's going to be du. So I just need to do this, and then once I've done it, I need to evaluate it again when s is 0. That's all it is. And you might say, wow, that's really simple. Yes, it is. It's incredibly simple. Not because it's some profound method, but it's just because all of the work has already been done in actually finding these Laplace transforms to begin with, right? We can't pull these Laplace transforms out of thin air. You have to do a bunch of work to derive them. But now that they're done, we have a shortcut, right? So this is so cool. And then, of course, 1 over u squared plus 1, that's a standard integral. That's arctan u. So we've got arctan u. The limits are s and infinity. Now, technically, guys, I'm being a bit cheeky here, and this is evaluated when s is 0. I'm being a bit cheeky because you should have a limit as maybe t or a different letter approaches infinity, and I should have that variable up there. But excuse me for not being quite so rigorous in this one, okay? So hopefully if you're watching this video, you're pretty happy with the idea that arctan of infinity, okay, I'm using that very loosely, is pi over 2. The limit as, let's say, x approaches infinity of arctan x is pi over 2, but we all know what I mean, minus arctan of s. And again, we're evaluating this when s is 0. And you guys can see it's super nice because all we've got is pi over 2 minus arctan of 0. And arctan of 0 is 0. So this is just pi over 2. So this is, again, I can't really emphasize enough how powerful this is. I've got a 20-minute long video doing this integral. We've just done it in like 3 minutes or less, right? So it's unbelievably quick. Again, not because it's some magical thing, but because all of the work in getting these results, like the Laplace transform of f of t over t, that has been done elsewhere. We've just pulled this out of thin air, but of course it's not actually come out of thin air. So that's why it's so quick. But really, really nice. Okay, let's look at one more. Okay, so we've got the integral from 0 to infinity of x to the power of 100 times e to the minus 2x. Now, this is just kind of a fun one because technically, if you try to do this with integration by parts, you would have to do integration by parts, and I'm not exaggerating, 100 times. You would have to do integration by parts 100 times in order to get this integral, right? Now, technically, there are quicker ways. You don't have to use integration by parts, but if you had like x e to the minus 2x, that's what you do. X squared e to the minus 2x, that's what you do. There are ways to do it without. I'm not being so hyperbolic that it's like it's that bad. It's that crazy. But yes, if you did do this with integration by parts, you would have to do integration by parts 100 times. But what we can do is we can realize this is actually a Laplace transform. This is a Laplace transform of t to the power of 100, okay, and it's evaluated when s is the number 2, okay, again, because the Laplace transform of t to the power of 100 is just the integral from 0 to infinity of t to the 100 times e to the minus 2s, or sorry, minus st, not 2s. I'm thinking about the question. E to the minus st is what I'm supposed to be saying there. st dt, okay? And again, we're evaluating it when s is the number 2. Now, what is the Laplace transform of t to the power of 100? I'm going to write this down as well because there's a standard formula for this. So the Laplace transform of t to the power of n is the gamma function of n plus 1 over s to the power of n plus 1. And in this case, because maybe you don't know what the gamma function is, maybe you don't know about it or you're not that confident with it, because n is a natural number here, we don't need to use the gamma function. In this case, we can use the factorials. So it's n factorial over s to the power of n plus 1. Okay, so don't be confused by the gamma function if you don't know much about that. We can use n factorial. So what we end up with, guys, is basically that we've got that this is equal to, so n is the number 100, so we've got 100 factorial divided by s to the power of 101. And again, this is evaluated when s is the number 2. And so what we have is 100 factorial divided by 2 to the power of 101. And of course, if you wanted to, maybe you could use a computer and you could try and get it as a decimal or something. But I don't think this is a nice number, but I just leave it like that because it's these are huge numbers. I don't even know if a computer would be able to do 100 factorial. I guess it could. But I just leave it like that, right? So that's the answer. Maybe it can simplify a little bit, I guess, but I wouldn't really bother with it. I think that's a completely fine way to leave it. So there's loads and loads of uses to this. please do let me know, guys, if you want to see more videos going through some integrals using Laplace transforms, because I'm addicted to it. I think it's so fun, and it's so satisfying because of how easy it is. And it's a great way, even if you don't like need to use this, it's a great way to revise the topic of Laplace transforms, because it keeps all those Laplace transforms in your head. So it's really, really, really good. But if you enjoyed the video, guys, please do subscribe, like, share, and all of that good stuff. And yeah, I'll see you in the next one. Cheers.